Hey guys, thanks for tuning into CMTEQ channel. This is tutorial number 7 on IDMT Relays calculations. Now by the end of this tutorial, you should be able to grasp a good understanding of how to solve IDMT Relays settings, timing when it comes to discriminations of protections of high voltage bus bar. And the problem statement goes as follows. Given the information above, calculate a suitable TMS settings for proper discriminative grading if the relay at D is to operate after 0.4 seconds for a fault on D. Relays A and C have a plug setting of 200%, as we can see, relay A and relay C. But relay B is at 175 and relay D is at 150%. Now, the way these bus bar arrangements are done is that a relay that is sitting near bus bar A here is protecting this bus bar. That's its primary goal. So the minute the current exceeds a specified limit, there is going to trip. But equally so, it will be protecting this bus bar here. But it will not do so until these relays that are wired next to this bus bar tripped first. So if there is a fault on bus bar D, that is the job for relay D here to trip. But if it fails or malfunction, takes too longer, then the bus bar, the relay C here, will then trip and isolate that part of the circuit. And it is the same that happen all the time over all the relays. This is why it's called discriminative grading. And the only reason that is possible is because they don't have the same operating time. So we'll see that because the first relay here is operating in 0.4 seconds. So we're going to use the grading margin, okay? So that will mean that every time we move from this relay to another, we're going to be adding the time. And that will mean that the last relay here on bus bar A will have a much longer time before it's triggered compared to the other previous relay. So that prevent them all from tripping at the same time, or prevent this relay here from tripping while relay C could have tripped just to protect bus bar D, putting the entire system offline. So we don't want that. We want the system to remain online for as long as possible, obviously, while it's safe to do so. Okay, now before wasting any further time, we have to start with the solution for this problem. And also, please don't forget to subscribe to my channel. I will really appreciate that. And also give the tutorial a thumbs up if you find anything useful in this tutorial. Now we go. So for the first relay D, that is for the fault on bus bar D. Okay, that is this bus bar. Now we know that the fault here is 5000 amp. The CT ratio is 200/1. PBS is 150%. Now we know that before we can calculate the IDMT relay times, so that is the tripping time and the actual time, there are other things that we need to calculate first. One of those is M, that is your multiple of settings. Now, M, the multiple of setting, is given by this formula here. M is equal to I fault over the CT ratio times your IN times your plug settings. We all know that. So everything is given here. We just need to fill up the formula. So this gives us the 5000 of the fault current over this ratio here times a nominal current of 1. That is your secondary of your CT current transformer, and your plug setting of 1.5. So we have an M of 16.66 here. Then what do we do with this M? Well, so we use this M to then calculate your tripping time TC. But the tripping time is informed by the IDMT characteristics curve. Now, since they did not specify which IDMT characteristics curve to use here, whether it's a very inverse, extremely inverse, or what have you, we then have to use the normal inverse characteristic. And the formula for the IDMT normal inverse characteristics is given by TC, that is equal to 3 over log of M here. So we then have to proceed and use that TC for the formula. But also note that because this is the first relay here, it is set to operate in 0.4 seconds. So that is the actual time. So no matter what, whenever there is a fault, a high fault current here on this bus bar, this relay here must trip in 0.4 seconds to clear it. So that's the actual operating time of this relay here. So what this means is we already have the actual time, TA of relay D, that is equal to 0.4, given there by the problem statement. So the only parameters that we're looking in terms of timing here is your TC and your TMS. So TMS is given by TA over TC. Since TA here is equal to 0.4, then we only need TC. But I just said earlier that TC is given by your characteristics curve. So the characteristics curve here is your 3 over log M, but M is 16.66. So we replace and we're getting a TC of 2.45. And solving for TMS, we have a TMS that will be equal to 0.163. Now these are the parameters for relay D for a possible short circuit current of 5000 amp occurring on bus bar D. So the parameters are, we have TC that is 2.45 seconds, and we have a TMS of 0.163, that's a time multiplier settings, and then we have an actual operating time of 0.4 seconds. So that is the parameter for relay D for a possible fault on bus bar D. Now we need to now move on to the next relay, that is relay C, the relay on bus bar C. Now it's become interesting here. Not only this relay C here must strip the power when there is a fault on C, it must also do so when there is a fault on D, assuming that relay D fails to open. Because if relay D is open, then relay C doesn't have to worry about bus bar D being isolated. So now to solve that, the trick is very simple. You have to first calculate for relay C for the fault on bus bar D. And to do that, you're going to use your M, your multiple of settings calculations. Instead of using the fault current on bus bar C, you're then going to use a fault current on bus bar D. That way you're going to have the timings that are going to be proportional to the fault current on bus bar D. I hope I'm making myself clear. The formula for M remains the same, but this time you're using the same fault on relay D. But look at the CT ratio we're using here. The CT ratio is for relay C, that is 250 over 1, and the plug setting is also for relay C, that is 2, the 200%. We're only making use of the fault current of bus bar D, okay? And that gives us a value of 10. We can then go ahead and replace it into the TC formula. So that gives us TC is equal to 3 over log of 10. So that is equal to 3 seconds. So that's the value of TC. We don't know the actual time. Now we got TC for this relay C for the fault at D. But we don't know what is TA, the actual time. But relay D, the TA here was given as 0.4. But how are we going to get the actual operating time for relay C? Now, since we are operating on a grading margin, that means 0.4 seconds is the actual time for each relay. So that is the time to be added. So what we're going to do is we're going to take the actual time for this relay here, that is 0.4, plus the actual time of this relay. We have to add them together, and that is going to give us 0.8 seconds. I hope it's clear. So this is a grading margin. So this relay here was operating in 0.4 seconds, and this one here also must operate in 0.4 seconds. That's a minimum actual operating time. But because it is a grading margin discrimination, so we have to add this relay time to this relay's time. So that gives us a total of 0.8 seconds. Now from here, we can then go ahead and calculate the TMS, which is the time multiplier settings, the same way we did here on this relay. And that is going to be very simple to calculate, since we know what is TA, that is 0.8, and TC is 3 seconds that we just calculate here, and we're getting a TMS of 0.2667. Now we have all the parameters for this relay for a fault on D. But now we need to calculate those relays parameters for a fault on C. And that fault is 9,000 amps. So we have to repeat the same calculations, this time using this current here. So that's going to be 9,000 divided by 200 over 1 times 2, and that gives us 18. And from here we can calculate TC, and TC is 3 over log of 18, and that gives us 2.3 seconds. That is the tripping time of this relay. Now that we've got TC, the only parameters now missing for this relay here is the actual time. Now, don't get confused now with what's going to happen here now. We have an actual time here that is based on the grading margin, and this actual time was used to calculate the TMS, and that was for the fault on D, and we have to do with the grading margin. But we now need to calculate the relay's actual time for its own fault, because this actual time of 0.8 here is if the fault occur on D, but it's not going to be the same actual time if the fault occur on its own bus bar C. That's a difference. Now to get that actual time, we then have to use the TC that we just calculated here with the TMS formula, and that is going to be using the previously calculated TMS here and the TC to calculate that actual time. Since TMS is TA over TC, we can then make TA the subject of this formula, so TA will be TC times TMS, and replacing that's going to give us 2.39 times 0.2667. Okay, just like here. And from here we can clearly see that TA is equal to 0.637 seconds. Okay, now you can see the difference here. Look at this TA, it's 0.63 seconds, and look at this one here, it's 0.8 seconds. So this TA here is much bigger compared to this one here, because this one need to respond for a fault on D, and also the fault on D is much lower than the fault on C. But as soon as there is a fault on its own bus bar, this relay must trip at this time. It doesn't matter what's going on here. The situation here might be a healthy situation, there's nothing going on, but if something arises here, this relay here cannot rely on the 0.8 actual time, but must rather have the 0.6 seconds. So that's the difference between the two actual time. I hope we are on the same page here, because it's much better when we all are on the same page. Now we're going to move on, and this time we now need to calculate for relay B, okay, for the fault on C, and also for relay B for the fault on B. Now moving on, we are now for relay B. This time we have now to first solve for the fault on bus bar C before we can solve for the fault on bus bar B. So relay B for fault at C, okay, that is a fault of 9,000 amp. We're going to once again repeat the same process with a multiple of settings. So that's going to be 9,000 divided by 501, because relay B here got a ratio of 500 over 1, and it has a plug settings of 175%. So that gives us a multiple of settings current M of 10.268. And this value here, we then going to calculate our TC. TC is then 3 over log of 10.268, and that gives us a value of 2.964 seconds. So that is the value of the tripping time for this relay here for a fault on bus bar C. But okay, we are not done here. We need the actual time. We need the actual time now. What will be the actual time here for this relay? Now remember, there are two types of actual time. So you've got one actual time for the fault on its own bus bar where this relay is located, and you have also an actual time for the fault on the other bus bar. So if the fault occurs on bus bar C, we must have an operating time for this relay. If the fault occurs on bus bar B, we also need to have an operating time that is different of the fault on bus bar C. That way it's not going to trigger at the same time or either one of the fault. So there must be a difference. Okay, so now how are we going to calculate the first one? Because this one we're doing for C. So the actual tripping time or the actual operating time for the fault on bus bar C will then be based on the grading margin. You guessed it. From which grading margin? Now, as you watching this tutorial, you can pause and rewind it. You'll see that when we were calculating for relay C here, okay, for its own bus bar, for a fault on its own bus bar, we got a TA on actual time of 0,637. So that is the actual time for the fault occurring on this bus bar. So it is from this time we then need to add the grading margin. So which means the grading margin for our relay B for the fault on relay C will be that 0,637 plus the 0.4 grading margin that we are adding for every relay. Okay, so we're taking that actual time of this relay here based on this fault on bus bar C, and we add a 0,4, and that gives us an actual time for this relay. Because remember, these relays must discriminate between the fault and one another. So it's taking account of two, the fault and the other relay as well, because they must never trip at the same time. Okay, so from there we now know the actual time. So this will then be much easier for us to calculate then the time multiplier settings. So the time multiplier setting will then be equal to TMS T over TC. That is 1,037 over the 2.964 seconds that we got there. And that gives us a 0,35 TMS. Now remember, this TMS here is going to be used to calculate the actual time for this relay B for a fault on bus bar B. Please remember that. That's how the procedure is working. The same way we use the TMS that we got when calculating this fault here for this relay D to calculate the actual time of this relay C for a fault on C is exactly the same procedure we're going to use to calculate this TMS that we are getting for the fault on C to calculate the actual time for the fault on B. I hope I'm making myself understand, because it's a bit tricky, but once you understand it, you'll know what's going on. Okay, so if you have any question, part of this is not making any sense, please drop a comment on the comment box. I'm going to attend to your comment as soon as I have time. Thank you for that. Okay, so we're going to move on now for the same relay, but this time for the fault on bus bar B. So again, once again, the same process apply. We calculate M and then we replace the values. So this time the fault is now 12,000. It's no longer 9,000. So that then gives us a value of M of 13.71. Okay. Remember, the same settings are left unchanged. The same relay setting are left unchanged here. The only thing that changed is the fault current, because we are now working on bus bar B. We can then go ahead and replace it into the TC formula. So that is 3 over log of 13.71, and that gives us a value of 2,64 seconds. Now we've got the value of TC. We can then go ahead and calculate the value of TA, the actual time. We already have the value of TMS that we calculated based on this relay on the fault on C, because remember, they have to discriminate with one another. That is why we're using the TMS that we calculate with that fault to now get the actual time for the fault on its own bus bar. So that gives us TMS is equal to T over TC. We then make TA the subject of the formula, so that gives us TA is equal to TC times TMS, and that gives us 2,64 times 0.35, and that gives us an actual time of 0,924 seconds. As you can see here, the same scenario we had on this relay here, that the actual time between the two was different, because now you can see that the actual time here, based on the grading margin, this one is higher compared to this one, because the 1 second actual time is protecting this bus bar that got a 9000 amps of fault current. But the 0.9, that's less than a second actual time, is for this bus bar B that got a fault current of 12,000 amps. So this is how they do the discriminations. So the higher the fault, the less time it must take to trip. The smaller the fault, the longer the time it must take to trip. So that is where these differences are coming from. Okay, now let's move on and finish off. This time we have to go for relay A, and again for the fault on bus bar B, and also for the fault on its own bus bar. Now to do that, we once again have to calculate our M multiple of settings, okay, for this relay. So now the fault on bus bar B is 12,000, and this relay A here also, just like relay B, have a CT ratio of 500, and this one here have a plug setting of 200% compared to relay B of 175%. So we got an M multiple of settings of 12, and thus will be then used to calculate our TC, and we get a TC value tripping time of 278 seconds. Okay, and then from here we can then calculate the actual time for this relay, okay, for the fault on B. And as we've done previously, we're going to use the grading margin, okay, and we're going to use a grading margin based on what? Based on this relay B, okay, actual time for the fault on this bus bar, and that is the 0.924 seconds we calculated here. So we're going to take this time here, we're going to add the grading margin of 0.4 on it, and that will be the actual time for this relay in case there is a fault on this bus bar and this relay failed to react. So we have to ensure that that time is bigger than this time. That's why we're adding the 0.4 grading margin. So that gives us a total time of 1.324 seconds. So that is now for the actual time for the fault on relay B. Now one more parameter we need to calculate here is TMS. So TMS will then be T over TC, that is 1.324 over 278. And that gives us a value of 0.476. And remember, we're going to use this TMS when we are going to calculate the actual time for this relay here, okay, for the fault on bus bar A, that is a 20,000 amp fault. Now we're done with this section here. We can then go ahead and move on to relay A for the fault on its own bus bar. Now once again, we calculate M, the multiple of settings, and completing the formula. So we've got 20,000, okay, divided by the ratio there, and the nominal current, and the 200% plug setting, and we're getting a value of 20, okay. And then the 20 here is going to be used into the TC formula, and we're going to find the TC of 2.306 seconds. We can then go ahead and calculate the value of TMS. That will be TA over TC, making TA the subject of the formula. TA will be TC times TMS. Okay, we have a TC of 2.306 that is going to be used, and then we have a TMS of 0.476 that we calculated there, and that gives us a TA actual time of 1.1 seconds. As you can see, this actual time here, okay, this actual time is smaller compared to this actual time there. And once again, you can see that the current on this bus bar is 12,000, okay, the fault current, and the current on this bus bar here is 20,000. So that's how the fault current is. So as you can see, the fault current on this bus bar is 12,000. That's why we have to react on a much longer time of 1.3 seconds. But when we come to the current of 20,000 here, we have to react on a much faster time as well of 1.1 second. So you have to distinguish how the fault current impact the tripping time of this relay. And you can never have a situation where you have a higher fault current on this bus bar B and then you've got a smaller fault current on bus bar A. It can never be, because this is a downstream flow. So this is a power supply, okay, your substation or your power plant generator. So the power is flowing this way, and as it's flowing this way, it's encountering, based on your per unit system, you're not going to have the same level of fault on the first bus bar up to the last bus bar, because there will be some voltage and impedance occurred into your system that's going to limit the current. Okay, so that is it for this tutorial. Please guys, if you found something useful in this tutorial, give it a thumbs up and subscribe to CMTEQ channel. Until next time, stay tuned for more tutorial like this. Cheers.